Hi everyone, welcome to Lab 11. This is our interference and diffraction lab where we're going to be looking at single slit, double slit interference patterns. But before we do that, I want to talk theory briefly so we can make sure we're all on the same page. So let's create a single slit here, and this is basically just a little cut in a piece of paper, and we can blast some light at it. And that light coming out of the top and bottom of this slit will have interesting properties if we were to project it onto a back wall. You can imagine that the top of this, as the light gets to the back wall, it's going to have a certain phase, and the bottom of this is going to have a certain phase also. And because of the way that light and waves work, sometimes those phases add up and sometimes they subtract from each other. So sometimes they're going to be out of phase with each other, create destructive interference, which looks like a dark spot. The two light beams kind of cancel each other out. Sometimes the two light beams are going to be completely in phase, perfectly, and they're going to create a light spot. And then there's a whole bunch of in-betweens. So this is what it's going to look like. This is kind of supposed to be a graph of intensity. It's going to look something like this. Boop. There we go, something like that. And this is going to be our single slit interference pattern. So there's going to be bright spots and bright spots and dark spots. And I don't want to dig into the math of this too much. I just want to use it to inform our next thing, which is going to be our double slit pattern. So here's our double slits. And we're going to do the same thing. We're going to blast light at this double slit pattern and see what happens. You can imagine that the same kind of thing is going to happen where we've got a light coming from the top slit, light coming from the bottom slit, and the phase that they're going to get to the backboard here is going to be different at different spots. At some spots they're going to be constructively interfering, at some spots they're going to be destructively interfering. But in general, they're going to be creating a pretty regular pattern where when they line up perfectly, they'll create a bright spot, and when they don't, they'll create a dark spot and somewhere in between. Now, the problem with this regular pattern is that we also have two individual single slits going on here that are going to exhibit the single slit pattern. So, unfortunately, the pattern is not quite that clear. It looks a lot more, well, interesting. Let me draw it out here. This is going to be the addition of these two patterns on top of each other. So I'm going to draw the single slit pattern, something like that. And then on top of that, I'm going to draw, or maybe inside of that, I'm going to draw the double slit pattern. And now let me erase the single slit pattern so you can see exactly what this is going to look like. And the net result of adding these two interference patterns together, and I'm going to create our central line here. And it's going to look something like this. So you're going to have a regular pattern from the double slit, where we're going to have, let's call this m equals 0. Then every other regular pattern is going to be m equals 1, m equals 2, m equals 3. And notice, by the way, that there are spots where the pattern is repeating, but it's going to be a dark spot because of the single slit patterns diminishing the light at that point. But we still have to kind of count it in that regular pattern that we were expecting. So let's talk about the double slit equation real fast. We can unpack this. D sine theta is equal to m lambda. Let's look at, this is our double slit, and if we talked about the distance between the two slits is going to be d. And this is from center to center of these two slits. The lambda in this case is the wavelength of the light that we're using. And again, we're going to create this interesting double slit pattern here. And as long as we are counting correctly, we can figure out which m we are on, which interval. The last piece of this is that sine of theta. Let me show you how we're going to determine that. Let's use m equals 4. I'll draw a line there. And theta is going to be this angle between the central line and our m equals 4 spot. Now, let me dig into this triangle a little bit more because we've got to figure out what theta is. We're not going to be able to measure theta. So here's our right triangle with theta here. But if we did some measurements, we could figure out like how far away from the central line it is on the backboard. We call that y maybe. And then we could also figure out how far away the double slits are from the backboard. Call that big L maybe. Now the problem is we're looking at sine of theta. So sine of theta is opposite over hypotenuse, and we don't quite know what the hypotenuse is. But this is where the small angle theorem can save us. Because this angle, this is of course not actually drawn to scale. This distance from the backboard should be quite large compared to this distance here. So this is a very small angle. And if we're using the small angle theorem, we could say that, well, this length is basically the same as this length here. Or that sine of theta is basically the same thing as tangent of theta is another way of saying that. So in this case, we could look at the sine of theta as the opposite over hypotenuse, or y over L. So I'm going to make that substitution in, and we're going to get our final big equation for the lab. And that is the equation that we're going to be using for the remainder of the lab here. If you were to make any of these measurements correctly, you could figure out what any of the missing pieces are with a little bit of algebra. Alright, I'll see you in the experiment.